2025.
Okay.
Time for questions. We're gonna stop at 30.
So 11:30, I should be.
11:38. You should.
Oh,
Oh,
okay.
sorry, 11:40.
Oh, okay.
11:40 is when all questions will be done.
Cool.
Okay. It's my pleasure to introduce Amelia Pompilio from here at UIC, who will be talking about divisible convex sets and P-uniform convexity.
Yeah. Oh, thanks. Oh, this is awesome. I don't have to think about what to do with my hands now because I'm holding stuff. Okay, so I owe you two definitions immediately. I'll be talking to you about divisible convex sets and P-uniform convexity. So first, on the left, you will see what David Hilbert looks like when he's not wearing a hat. And then on the right, you'll see the two things that you need in order to define a Hilbert geometry. So you start with some omega, which is just a convex set. It doesn't have to be strictly convex, but in this talk, they will be. And if you want to know the distance between 2 points x and y in that set, what you do is you draw the straight line between them, and then you look at A and B, the 2 points where that line intersects the boundary. So one benefit of working on this stuff is that I never get this formula wrong now, and now you won't either, because here's the mnemonic. You actually can't see the laser, so this is fine. I'll just have to do it with my hands. So the formula is long times long over short times short. So long is the segment A to Y. The other long one is X to B, and the short ones are A to X and Y to B. So as the points X and Y get closer to the boundary, the distance gets larger. Okay. Okay, so this story begins with this paper of Kelly and Strauss from 1958, where they talk about curvature in Hilbert geometries, which notion of curvature, Busemann curvature, which you can read that in squint if you like, but here's some visuals. So Busemann curvature has to do with looking at some base point, which will be like the lower left corner in these diagrams. You look at two lines, geodesics, coming out of that. And then you look at the midpoints of each of those line segments. You look at the distance between the midpoints. So in the middle, that's like the flat case. If you double the length of like between the midpoints, you should get exactly the length of the longer side. And if doubling undershoots that, then you are negatively Busemann curved. And if you overshoot that, you are positively Busemann curved. So their result was that if the curvature is determinate everywhere, which just means in a neighborhood, you get the same sign of curvature everywhere, so no mixed positive and negative triangles. If the curvature is determinate everywhere, then C, the set that you started with, the convex thing, is an ellipse, and the Hilbert geometry that you get from that set is hyperbolic. Okay. So this d omega, this Hilbert metric, has the good taste of coming from a Finsler metric on omega. Spicy quote due to Marquise. Okay, so what's a Finsler manifold roughly? You get some manifold that has this like asymmetric Minkowski functional thing on it. So I'll describe that briefly with the photo as well. So you have some base point on the right here that's going to be x. And if you want to know the length of some vector in this, you look at how much you would have to scale that vector in order to make it touch the boundary. So in this example, you would have to double the length of, oh, it kind of works. No, never mind. I'll just gesture from afar. You would have to multiply by 2 in order to make that thing reach the boundary. So its length should be 1/2. Okay, and then how does that relate to the Hilbert metric? Well, if you differentiate the Hilbert metric, you can see it better with a picture, but you can think of sort of averaging the forward direction of this Minkowski functional thing and the backwards direction. So x is there, this vector v is going up, and it goes to some boundary point p plus, and then p minus the other way. So you symmetrize, and you can get to that. Okay, Marquise also says that you can think of these as damaged, non-positively curved manifolds. By the way, if you Google Ludovic Marquise, you will find that there is also a famous French rodeo athlete by the same name. And after talking to Jeff on Friday, he informed me that he has actually met Marquise. They are not the same person, but they've never both been in the same room. Okay, so now what's a divisible convex set? You have some omega in projective space where you have some discrete group gamma acting co-compactly on it. So that's the divisible part. And this is a thing that's known. So at the beginning, we talked about Buseman curvature and how you're only going to be determinate curvature at all if you are an ellipse. In fact, you'll be negatively curved. And so we might wonder, okay, how about any sort of cat K property that they might have? It turns out that you only get to be cat anything if omega is an ellipse as well. So when you're strictly convex, though, you still get some negative curvature things happening. So for example, you're uniquely geodesic. Also, fun fact, that's an exercise that Jeff gave me when he was bored, potentially, or I guess so I wouldn't be bored. So that was an exercise that could be fun to talk about as a question after this. You also get that they're going to be Gromov hyperbolic if you're strictly convex again. And also the geodesic flow on it is going to be an Asaf. That's like the only dynamicsy thing that I'll say for the rest of this talk. So sort of the big question might be, is there some notion of curvature that omega does satisfy? And so that's going to bring us to P uniform convexity. So what is P uniform convexity? It has to do with bounding this modulus of convexity from below, and I'll explain what that is now. So this modulus of convexity, this delta of epsilon, is this quantity here. You look at vectors that are epsilon apart, then you look at their average, and you see how far away that average is from the boundary. So that's a lot of stuff. Let's look at an example. So just pretend that you are in the simple example of a circle. So you would have your base point in the middle in this case. The vectors x and y are both going to be of length 1. Also, in general, when we're going to look at the modulus of convexity of some sort of shape, it's always okay just to look at vectors of length 1. So we'll do that, makes our life a little bit easier. So these are epsilon apart, and then you can compute x plus y over 2. In this case, doing some Euclidean geometry. So again, x is like length 1. The little right triangle has epsilon over 2 side length, and you can compute the red line. So you'll get this value. So that's the length of the red thing, and we want to know how far away is that from the edge of the circle. So we do 1 minus that quantity, and that's our modulus of convexity there. Okay, so on the left, that's something that is P uniformly convex because the modulus is bounded from below by this constant C times epsilon to some value of P for P 2 or greater. So on the right, that's something that's not P uniformly convex because there's no gap. Okay. All right, so there it is, the statement of our theorem. No longer theorem in progress, very exciting. So yay, thanks for wooing. Yeah, if you have a strictly you have a strictly convex divisible domain, then for any base point that you pick, that space with its Minkowski functional base at that point is going to be beta uniformly convex. So I have some special things to say about what beta is in particular. And so beta is still in the same range, and it has this special relationship with something else that's alpha that I'll talk about here shortly. And also, in general, this notion of P uniform convexity was put forth by this guy Shin Ichioda in order to like generalize cat K things. So we're like, okay, maybe if they're not cat K, are they at least this? Okay, so let's back up and talk about this alpha and beta. So Benoit has done a lot of surveying of these things, and he showed that for one of these domains, its boundary is going to be alpha holder. So you get some alpha that's going to be between 0 and 1. And then Guichard comes along and introduces the notion of beta convexity. And so that's this inequality, which is better represented by this picture here. It's saying that that dotted distance from x to the tangent plane down there is bounded below by that red segment to some power of beta. So that's going to give us that you can fit like a polynomial in beta below these curves, wherever you look. And then also the upshot is that these convex divisible domains are beta convex, so we can use that. Okay, oh yeah, and then finally someone came along and translated that one paper, so that's Anton Lukianenko. So I owe him my life, or at least a very nice email after this is all over. Okay, so for the rest of the time, okay, I'd like to talk about one of the cases of the proof of this. And I'll explain a little bit more as we go on why there have to be multiple cases, and all that jazz. Okay, so we start with just some portion of our omega here pictured in red. And we're going to look at two vectors that are epsilon apart. So that segment is going to be length epsilon. And that big red point in the middle is the midpoint of that segment, which will be useful for us here shortly. So beta convexity from Guichard gives us that we have this curve completely below, and they are both tangent at this point, 0, -h. Okay. And so what we're going to do is sort of compare these two curves to each other and compare their moduli of convexity as we go. So we're going to project everything down, and instead of dealing with X and Y and everything on the red curve, we're going to deal with Z and W on the blue curve. Okay, and then so notice that up top, it says that this is the theta less than 45 case. So in order to get things into coordinates all nice like this, we had to do some linear transformations. And so in doing that, we lose some control over how steep that line segment is going to be in our picture. So we kind of arbitrarily cut it off at some point when things start getting too steep, and we handle that case differently. Okay, and then theta is that, like, how steep that segment is in comparison to the tangent line. Okay, so recall the Minkowski functional thing where we're looking at scaling factors and how far away you are from the boundary. So A is whatever scaling factor it's going to take to go from the big red dot in the middle to 0, -h. And then B is the same one, but for the blue curve instead. Okay, so it should take a larger scaling factor to move the red point down to the bottom of this picture than it does for the blue point. So that should mean that 1 over those things has this relation. Okay. So then the modulus of convexity is saying every vector that touches the boundary is going to have length 1. So we want to do 1 minus this quantity here. And that'll give us that if we can compute the modulus of convexity for this beta convex thing, we will successfully bound the thing that we want from below. Okay, so we shove that over there. Great. Yes, so that's our big idea, I suppose, for this. So we want to compute what we need in order to get there. It becomes this quantity here after some calculus, I suppose. Okay, and so we need to do a comparison of norms just because we want things to be in terms of epsilon at the end of this, and currently things are in terms of this parameter t as we're comparing. And so we can do that, and just notice here that we do take cosine at some point. So if you get that segment to be too steep, you're going to lose information, and we want to make sure that this is not going to go to 0. Okay, so there we go. Yeah, you end up, I wish I had the laser here, but we do end up getting that the modulus of convexity that we wanted for omega is greater than some constant c times epsilon to the specific power of beta in the end. So it is beta uniformly convex. Okay, and then, this would have been good to have on its own slide, but going back to the beginning as well, we get our theorem is also true for the Finsler metric here, because if it's true for the Minkowski one, we symmetrize, take the average of the forward and backward Minkowski functionals, sort of, and you get the result for that as well. Okay, thanks. Okay, I think I kind of sped through that. I was like going for 15 minutes with 5 minutes of questions, but
Yeah, that's okay. Does anybody have any questions? Yeah.
No. Oh, no, I was just trying to put that somewhere because I heard people were doing that. Yeah, thanks. Well, I do, just in case I finished early, I did put one more slide just for the other case. So I'll spend a couple minutes talking about this. So we do need a slightly different configuration when that segment is going to start getting steeper. So instead, you kind of do this hockey stick thing, which you can fit strictly convex. This is all okay. And you can do a similar computation where you're interested in the blue point down there, and you can do this comparison stuff and still get that your modulus of convexity is going to be bounded away from 0. And I don't think I included anything after that. Oh, yeah, okay, so here's all the stuff